You made it to the last day of the show. Congratulations. I think many of you came to what I consider to be the largest and most important trade show in the chemical industry, looking for something very important. Answers, insights, ideas. Hoping to discover that one thing that can make a really big impact on your equipment, on your site, on your business. My name is Nick Rentzelos. I'm with a company called Flowserve, Innomag. Flowserve has been making chemical process pumps for the better part of, I don't know, maybe 100 years, 150 years, something like that. I personally have been in the chemical process pump business for just over 3 decades. And I've come to the show today to share with you what I consider to be the one thing that can have the biggest impact on the efficiency, on the reliability, on the overall effectiveness of your chemical process pumps. And this thing, ironically, is something that most operators and engineers don't think a lot about. It's actually not even part of the pump itself. It's actually the connection between the pump and the motor. And for most of the chemical process pumps operating in the world today, that connection is a physical one, meaning torque is transmitted from the motor to the impeller using a direct physical connection. And the pump, in order to accommodate this direct physical connection, essentially needs 2 things. First, because the shaft has to penetrate the pump body, and one moment, is that better? Yeah. Because the shaft has to penetrate the pump body and physically attach to the impeller, obviously you need some kind of shaft seal to plug the hole and contain the fluid. And if you're lucky, you can get away with 1 seal, but many applications, as you know, require a second and sometimes even a third mechanical seal and the use of some kind of flush plan that can range from the simple to the complex. The second thing you need in order to keep loads off those seal faces and to keep them perfectly aligned is a good set of axial and radial ball bearings. And many people consider ball bearings to be the heart of the pump, which would make the oil the lifeblood, which means you need 2 more high-quality seals to keep the oil in and the contaminants out. You need a device to keep the oil at a proper level, and you need a robust maintenance program to keep that oil in proper condition. Now, in order to prevent vibration, deflection, and premature failure of the shaft seals and the ball bearings, you need to invest the time, equipment, and expertise required to align the shaft of the motor with the shaft of the pump within 0.05 millimeters. Now, to give you an idea of how small that is half the thickness of a human hair, and it's not enough to just establish a near perfect alignment. You need to maintain it over time, which is why you need reinforced base plates and to keep nozzle loads to an absolute minimum. Finally, the coupling itself, that connection is an exposed rotating element, so you need a coupling guard to keep operators safe. So as you can see, those 2 components, ball bearings and shaft seals, account for all of the complexity of a chemical process pump. They account for the vast majority of its installation costs, at least 50% of the footprint, and all just to achieve a small fraction of the operating range, because at the end of the day, it's the shaft seals and ball bearings that limit the reliable operation of chemical process pumps to essentially one duty point called BEP. Over time, those 2 components will account for nearly 80% of all pump failures. They will account for nearly every man-hour of maintenance, all leaks and fugitive emissions, obviously, and a good portion of the working capital you have tied up in spare parts inventory. This is the total cost of owning and operating a chemical process pump with shaft seals and ball bearings, and it all started with that, the connection. The one thing that can start a chain reaction of design decisions that can have huge implications on the overall effectiveness of your chemical process pumps. But what if? What if we can use a different kind of coupling? What if we can use a coupling that kept the pump and motor physically isolated from each other? A coupling that can transfer torque from the motor to the impeller without a direct physical connection or penetration through the pump body. A coupling like this one, for example. This is a magnetic coupling. It's a very simple device. As you can see, it's just a set of permanent magnets on the outside of the pump mounted directly to the motor, and a set of permanent magnets on the inside of the pump mounted directly to the impeller. And it's the combination, the attraction and repulsion between these two sets of magnets that allows the impeller to spin completely in sync with the motor without having to make any contact with it. So the benefits of using a magnetic coupling is it allows you to eliminate the two most critical components in a chemical process pump, the shaft seals and the ball bearings, and with them, all of the problems, all of the maintenance, all of the leaks and fugitive emissions, a good portion of the spare parts that you have in inventory, a lot of the installation costs, all the limitations, the complexity, and last but not least, 50% of the footprint. So what do we have left when we strip all of those things away? We have a chemical process pump in every sense of the word. It's horizontal, single stage, end suction, centerline discharge, back pull-out, foot mounted, overhung, dimensionally and hydraulically compatible to ANSI B73 or ISO 2858, just like any other chemical process pump. You would use it just like any other, inside for applications that are inside its operating envelope. And we're going to talk a little bit about that operating envelope a little bit later. So this is not the new and crazy idea that I came to ACHEMA this year to share with you. We figured out how to pump without shaft seals and ball bearings more than 75 years ago. But the technology back then was new and fairly limited, and it was used only as a last resort for the most extreme hard-to-seal applications. Believe it or not, it was considered highly specialized equipment back then. But we've come a long way since then, and today, over 40% of all the chemical process pumps sold in the world are sealless. And as this paradigm shift continues, and as the adoption of the technology accelerates, more and more end users now have what I call a sealless-first mindset. And it's a very simple idea. It just means that as an end user, I'm keenly aware of the impact shaft seals and ball bearings have on the reliability, on the safety, on the total cost of ownership, on the overall effectiveness of my chemical process pumps. And as such, the very first step in my pump selection process is going to be to determine if I need them at all. So what does Seallessfirst look like in the field? This, with permission, was cut and pasted directly out of a pump selection guidebook of a Tier 1 operator in the United States. And as you can see, the very first question they ask themselves when trying to find the right pump for the job is not what are we pumping? The first question is the application inside the operating envelope of a standard sealless pump? And if it is, use it regardless of what we're pumping. So, how do we explain such a dramatic shift from specialized to mainstream? How do we explain the shift from sealless as a last choice to sealless as a first choice? The answer is removing shaft seals and ball bearings simply make chemical process pumps better at what matters most to end users. And in my job, I have the tremendous fortune of being able to travel the world and meet with lots of end users of chemical process pumps. And it turns out that to one degree or another, they all essentially care about the same 6 things. For example, the safety of their operators and the impact their operations have on the environment. So let's dig into each one of these. As you know, the typical chemical process pump needs liquid to continuously pass through its seal faces in order to keep them cool and lubricated. In other words, the typical chemical process pump doesn't just leak, it leaks continuously and by design. And those small leaks, which you can't even see, you need special equipment called sniffers to detect them. They account for more than 2,000 tons of fugitive VOC emissions every year. So if you think about it, the typical chemical process pump essentially gives you 2 options. Small leaks when it works, big leaks when it fails. But a sealless pump, like Innomag, for example, uses a magnetic coupling. And like we said earlier, with a magnetic coupling, you're able to transfer torque from the motor to the impeller without a direct physical connection or penetration through the pump body, which means that the liquid section of the pump remains hermetically sealed. This is good because it means it doesn't leak, it improves operator safety, it reduces your impact on the environment, and it makes it more cost-effective. But at Flowserve, we don't stop there. We take operator safety to a whole new level. Innomag is the safest chemical process pump because it is the only mag drive to which you can simply bolt on an optional second magnetic coupling. so that not only is the liquid section of the pump hermetically sealed, providing the first layer of protection, but now for the first time ever, the drive section of the pump is also hermetically sealed, providing a second layer of protection, and all, believe it or not, within a standard ANSI or ISO footprint. This is called dual drive, and it is the world's first mag drive pump with true secondary containment. And when I say true secondary containment, it means that it has to pass 4 tests. First, it has to be absolute or hermetically sealed. Second, it has to be fully redundant. Third, it cannot wear during normal operation, leaving you wondering how much protection, if any, you have left when you need it most. And most important, it's got to be completely isolated from the forces and the failure modes of the pump and the primary seal, which means no leaks when it works, and more importantly, no leaks even if it fails. Because your operators deserve to be more than just safe, they deserve to be fail-safe. So where would you use dual drive? Naturally, when I use words like true secondary containment or fail-safe, people think of the most extreme applications. Applications that can kill you, applications that can burn you or blind you, applications that can cause cancer, respiratory failure, or organ damage. But here's the thing. This is not the SDS for arsenic. It's not the SDS for potassium cyanide or some fancy exotic pesticide. These are the images and the hazard statements that you're going to find on the SDSs for 95% of the chemicals that you use chemical process pumps for. Even at relatively low concentrations, things like sulfuric acid, hydrochloric acid, sodium hydroxide, sodium hypochlorite, even water at high temperature and high pressure can put operators in harm's way in a containment breach. And when we designed dual drive, our intention was not to protect a small group of operators running extreme applications. We wanted to protect as many as we can. So we needed to make fail-safe, cost-effective, and simple. So what does it take to transform your chemical process pumps from safe to fail-safe? All it takes is for you to bolt on a hermetically sealed dual drive unit that starts at around $1,000 US. So when we ask the question, where do we use dual drive, when it's that easy and that cost-effective to make your operators fail-safe, the answer is obvious: everywhere. Let's go further into what matters most to end users, like, for example, reliability. And most of the people in this room, I would imagine, are engineers, so they'll know what I mean when I say to improve the reliability of a pump or any other machine, you need to identify its weaknesses and try to eliminate them or at least reduce your dependency on them. Well, as we said earlier, shaft seals and ball bearings account for nearly 80% of all pump failures. So clearly they're the weakest link, and Innomag eliminates them both. But if we truly want to improve reliability, we need to take a good hard look at sealless pumps as well and find out what their weaknesses are. And it turns out their greatest weakness is their greatest strength. They're fully enclosed, they're hermetically sealed, which is great because they don't leak. But that also means that they must rely on the very fluid that they're pumping for cooling and lubrication. It's a concept called process lubrication, and it only works if the process fluid that you're using as a lubricant is clean and a liquid, which requires ideal system conditions and clean services. And here's the problem. In the real world, there's no such thing as ideal system conditions, and the only kinds of applications I've seen are dirty and less dirty. Applications with solids that are on the data sheet and applications with solids and contaminants that are not on the data sheet. So for that reason, a breakdown of process lubrication, just because the process fluid becomes contaminated, vaporized, or simply runs dry altogether, is the #1 root cause of failure for every single sealless pump failure. Think about that for a second. One thing causes nearly every single failure. When I hear that, I think there's some good news in that because it simplifies my buying process. It simplifies my pump selection process. If I'm shopping around for a sealless pump, all I need to do is walk down the hall and ask the people at the booth one simple question. What are you doing better than your competition to improve or address the problem of process lubrication, the #1 root cause of failure? And whoever gives you the best answer, that's the pump you should buy, period. That's the good news. Here's my answer to that question. Innomag addresses the problem of process lubrication in two ways. First, in the axial direction. As you know, centrifugal pumps essentially generate two kinds of forces, radial and axial. But axial are 10 to 15 times larger than radial forces, which means that axial thrust bearings must carry 90% of the total bearing load acting on the pump. Now, to give you a sense of magnitude, that's a force of approximately 2,000 pounds or 8 to 9 kilonewtons. That's like taking nearly the weight of a small car, balancing it on the part the size of a coaster, and spinning it 50 to 60 times per second. That would be a challenge for any bearing, let alone one that's process lubricated, where the only thing separating success from failure is a thin film of the very fluid that you're pumping. Innomag is more reliable not because it has better thrust bearings, but because it has no thrust bearings. Not because it can better tolerate thrust, but because it completely eliminates it. It's a system we call thrust balancing, and it's a very simple system that's designed to respond instantaneously and automatically to any forward thrust action with an equal and opposite hydraulic reaction. The forces cancel each other out, and the result is zero net thrust. So by eliminating axial thrust, you eliminate 90% of the total bearing load acting on the pump, which is great. But more important than that, when you're talking about a sealless pump, you're reducing the pump's dependency on process lubrication by 90%. So real quickly, how does this work? Here's a cross-section of an Innomag pump. You can see the casing, the suction, and the discharge. You see the black thing in the middle is the impeller with the integrated magnets on it. Outside of the impeller, we have the outer magnet. Here we have the motor adapter, and here is where you would connect a motor, a close-coupled motor. So most of the fluid, obviously, is going to go into the suction and out the discharge. But a small portion of it is going to go and work itself around the impeller and flush all the way to suction. So how do we achieve thrust balancing? Well, we look at the process fluid in a whole different way. Instead of like most sealless pumps that use the process fluid as a lubricant, we use it as a hydraulic fluid. And we use the impeller as a control valve. And as you can see, our impeller is designed to float axially along the shaft. And as it floats and moves back and forth, it opens and closes the valve, or the variable orifice that's located here between the stationary shaft and the moving impeller. And as you can see, as the impeller moves forward, the variable orifice opens, relieving the hydraulic pressure behind the impeller, letting it come back. And as the impeller comes back, that orifice closes, building up the hydraulic pressure behind the impeller, pushing it forward. So these constant micro movements is the impeller trying to find its happy place right in the middle with zero net thrust, where all the axial thrust completely cancels out. In the radial direction is the second part of our solution. It accounts for the remaining 10% of bearing load or process load, and we do two things. Number one, we designed a specially modified concentric volute to keep radial loads lower and more uniformly distributed throughout the curve instead of just at BEP. That's number one. Number two, we created a special pressure chamber inside the pump we call the green zone. And that green zone was designed essentially to do one thing. It is to keep the portion of the process fluid that's inside of it at any given point in time a clean liquid. We do it by filtering out any contaminants and by keeping the pressure inside the green zone specifically above the vapor pressure of the fluid. And by isolating the radial bushing inside the green zone, and again, the radial bushing accounts for the remaining 10% of the load, we make sure that it stays cool and lubricated when you're in the middle of a system upset, when you're pumping a volatile fluid, or when you're pumping solids. So yes, thrust balancing was our answer to the problem of process lubrication, and in answering, one of the beautiful side benefits of that was we created the world's first sealless pump that can handle significant solids, 30 to 40% concentration by volume, particle size limited only by what can fit through the enclosed impeller. So again, how do we do that? The way we do it is by making sure that the majority of the solids that we're pumping stay in the volute where they cannot cause any damage. So we use a a filter, a dynamic non-clogging filter made up of two coaxial silicon carbide rings with a very tight running clearance. One is stationary on the containment shell and one is rotating on the impeller. And the clearance between those two rings is about 0.1 millimeters. So it prevents any contaminant or any solid that's larger than 0.1 millimeters from entering the critical back section of the pump where it can cause damage. Anything smaller than 0.1 millimeters will make it through those rings and find themselves in a passageway that's 25 times larger than the contaminant, and it'll quickly and safely flush it out to suction. What matters to them is maintenance, because according to HI, maintenance accounts for more than 25% of the total cost of ownership. And every single man-hour is accounted for by shaft seals and ball bearings, and Innomag eliminates them both. In fact, studies have shown that in order to maximize efficiency, minimize downtime, and guarantee environmental compliance, a typical chemical process pump essentially needs 35 man-hours per year per pump to accomplish. Innomag needs exactly zero. Zero preventative maintenance. There is no seal replacement. There is no shaft alignment. There is no impeller adjustment. It does not need a sniffer to detect leaks. It doesn't even need an oil change. And bushings that are hydrodynamic made of silicon carbide that effectively never wear out. On top of that, it has a simple, user-friendly design that makes break-fix type repairs go fast and easy. If you just look at the long list of specialized equipment and tools that a typical chemical process pump needs, and hours on the workbench in the shop of precision assembly by trained operators. Innomag, on the other hand, can be disassembled, fixed, and reassembled in under 30 minutes with essentially just that. What matters is efficiency. And again, according to HI, the cost of energy makes up 40% of the total cost of owning a pump. And when you compare Innomag against the most efficient alternative in 3 different pump categories, you'll see that a typical metallic sealless pump like a can motor pump or a metallic mag drive pump requires up to 50% more energy to do the exact same amount of work, the same exact duty point. A typical non-metallic sealless pump will require on average 25% more energy, and even a typical chemical process pump with a single cartridge seal will consume on average 10% more energy than an Innomag pump, but that's assuming that it's perfectly adjusted and perfectly maintained. But nobody spends 35 man-hours per year per pump on preventative maintenance, and as a result, the efficiency of a typical chemical process pump will degrade by as much as 25% over the course of its lifetime. Innomag is not only more efficient on day one, its efficiency and reliability do not continuously degrade over time due to lack of attention or wear and tear. Now, efficiency is important for yet another reason, and in my opinion, when you're talking about a smaller chemical process pump, this is an even more important reason than the cost of energy, believe it or not. If you think about what efficiency is telling you, what is it measuring? It's measuring how much energy is used, but conversely, it's telling you how much energy is wasted. It's telling you how much of that energy is converted to heat and transferred almost entirely to a fixed volume of fluid inside the pump during an upset condition like deadheading, for example. It is a measure of how much more likely it is that that fluid will go from a liquid to a vapor during an upset condition, the same fluid that's used to lubricate seal faces and bushings. So if you think about it, efficiency is a measure of reliability, or more specifically, upset forgiveness. And all things being equal, the more efficient your chemical process pump is, the more reliable it's going to be. And this is, thrust balancing allows Innomag to operate with less friction and less internal recirculation, which is great because during normal operating conditions, it uses less energy. But more important, during an upset condition, it means that it's adding less heat to a fixed volume of fluid, making it less likely to vaporize. And here's the same chart that shows the power consumed by those same 3 pumps when they're doing no work, zero flow. And as you can see, those 3 pumps put anywhere between 2 to 3 times more heat and energy into a fixed volume of fluid during an upset condition, and making it that much more likely to vaporize. What matters is versatility. Versatility comes in two forms, material versatility and hydraulic versatility. So let's look at material first. The typical chemical process pump comes in over 10 standard material options to achieve a broad range of chemical resistance up to 370 degrees C or so. Innomag has all those options as well, but our most popular configuration is this one, a carbon fiber reinforced fluoropolymer lined ductile iron that can provide almost universal chemical resistance up to 121 degrees C. And unlike a metallic pump, where the material selection is critical based on the specific application in order to minimize corrosion and achieve a reasonable pump life, with Innomag you have zero corrosion because it is a non-metallic material, wetted material. But you might be looking at this and saying, well, 121C is a lot lower than 370C. What gives? Well, it turns out that when you look at all the chemical applications that you would use a chemical process pump for, it turns out that 90% of them are under 121C. 90% of them are under 360 cubic meters an hour. 90% of them are under 150 meters of head. And most of them require less than 25 bar of maximum operating pressure. So when you're asking yourself the question, is the application inside the operating envelope of a standard sealless pump, the answer is not only yes. The answer is yes with one material. So the other kind of versatility is hydraulic versatility. And as we said earlier, a typical chemical process pump was designed essentially to operate reliably only at one duty point called BEP. But the problem is chemical process pumps in the field rarely operate at BEP. And if you go outside of a small operating window of 80 to 110% of BEP, statistically, your reliability as measured by MTBF will fall nearly in half. Innomag was specifically designed to run reliably throughout its entire operating range. On the left, as long as you have enough minimum thermal flow, and on the right, as long as your system is generating enough NPSH, you're on the curve and you're generating pressure, you can run anywhere in the middle you want without any meaningful reduction in reliability. So let's put it all together. We have a pump that can operate practically anywhere on the curve, come in only one material of construction with universal chemical resistance. So now a single pump model can cover a wider range of duty points and services, which means you as an end user can now start to standardize your pump population on fewer pump models and reduce and simplify your spare parts inventory. Finally, initial cost, my favorite part. This is where most pump manufacturers will come up here and tell you that initial cost does not matter. The only thing that matters is total cost of ownership. Well, they're wrong. According to HI, it makes up for 20% of the total cost of ownership. And if you look at installed costs, it's made up essentially of two things, the cost of the pump itself and the cost to install it, which sometimes can be as much, if not more, than the cost of the pump. And those installation costs are all driven by things like couplings, guards, base plates, flush plans, lube systems, shaft alignment, field balancing, the need for all of which is driven by shaft seals and ball bearings, and Innomag eliminates them both. So when you look at the installed cost of an Innomag pump against an exotic alloy chemical process pump with double seal and flush plan, or a high-end can motor pump or metallic mag drive, it is easily half the price. But more importantly, even when you compare it against a typical chemical process pump in 316 or alloy 20 with a single cartridge seal, it's very, very competitive despite its long-term cost of ownership advantages. So, last slide. Let's put it all together. We have a pump that is hydraulically and dimensionally compliant to ANSI B73 or ISO 2858 standards, that is not only safe, but it's fail-safe, that is more reliable, that has a smaller footprint, that is a simple, more user-friendly design that aligns with the motor instantly without special equipment or expertise, does not leak, does not need maintenance, operates practically anywhere on the curve, comes in only one material of construction with near universal chemical resistance, is competitively priced, ships from stock in 5 days or less with 98% on-time delivery. This is the compelling value proposition that's driving the sealless paradigm shift. Thank you very much. I want to just give you my last slide here. This is not necessarily the most conducive area for Q&A. I would love to connect with you one-on-one. We can meet at the booth, the red booth behind, or in the area over here. If you scan the QR code, it'll bring up the email application on your telephone. Send me an email, say hello. I'll give you a copy of the presentation. And more importantly, we can set up a meeting where I can bring live demo pumps that show you thrust balancing and the world's first and only mag drive pump that can handle solids, and put it right on your conference room table and show your entire team. So reach out. Thank you so much.